Question number 71. If for the reaction 2A in the liquid state is getting changed into 4B in the gaseous state, delta U and delta S respectively are 1.2 kilocalorie, that's the value of delta U, and the value of delta S is 10 calorie per Kelvin. The temperature is given at 300 Kelvin. Then delta G for the given reaction is. We know that whatever be the reaction, suppose this reaction is 2A getting changed into 4B as per the given reaction I have written here, and we know that delta G is equal to delta H minus T delta S. In the question, if you look once again, you will identify that the value of delta S is given, but the value of delta H is not given. It means we need to find it out, and the value of delta H can be calculated with the help of the given value of delta U. The relation between delta U and delta H is delta H is equal to delta U plus delta NGRT. This is the relation, and delta U value is given, that is 1.2 kilocalorie. We'll change it in calories because the value of delta S is also given in calories. That's why I'm changing it. This is 1.2 kilocalorie. It becomes 1200 calorie plus delta Ng, number of gaseous moles which are changing here, N2 minus N1. 4 are the gaseous moles of product, and reactant is in liquid state. That's why it is 0. So delta Ng is 4. R value in calories, the value of R is 1.98, or simply 2 calorie per Kelvin that I have taken. Multiply temperature to it. What is the temperature? That's 300 Kelvin. It would be equal to 1200 plus 4 2s are 8, 3s are 24. It becomes 3600 calorie. We have delta H value now, so we can find out delta G also. Delta G is equals to 3600 minus T into delta S, that is 10. So it becomes 3000. 3600 minus 3000 is 600 calorie. And where the 600 is given? 600 is given here in option 1. So the answer for this question becomes option 1. After that, question number 72. For a sample of n mole of a perfect gas at constant temperature T, temperature that's in Kelvin, when its volume is changed from V1 to V2, the entropy change is given by. I have a simple formula to find out the delta S value. This delta S value is equal to N CV, specific heat at constant volume, ln T2 by T1, this is showing the temperature change, plus NR ln V2 by V1. This would be. Now, as the process is taking place at constant temperature, it means change in temperature is 0, and that's why this whole term can be neglected, and that's why this delta S is equal to NR log V2 by V1. The simple thing. On the basis of this, which option is correct? Option 4 is the correct option. That's why you should choose option 4 as the correct option for this question. After that, question number 73. Which one of the following pairs of solution is not an acidic buffer? How it is prepared? It is basically a mixture of a weak acid with the salt of that weak acid with a strong base. Then the mixture of these two is termed as acidic buffer. We need to just check the options here to find out the correct one. HCN, weak acid, NaCN, the salt of this weak acid HCN with NaOH, a strong base. It means it is an acidic buffer. Further, H3PO4, weak acid, salt of this weak acid with NaOH is Na3PO4, that's why it is also acidic buffer. H2SO4 and Na2SO4. H2SO4 is a strong acid, not the weak acid. And that's why I'm just ignoring this. Further, next option, CH3COH, weak acid, and the salt of this weak acid with a strong base, NaOH. It's given here. That's why this is also acidic buffer. So the one mixture is there which is not an acidic buffer, and that is given here in option 3. So just choose option 3 as your correct answer. After that, question number 74. If the concentration of calcium ions in the reaction, we have this reaction at equilibrium in which calcium ions and phosphate ions are formed, and in this case calcium ion concentration is decreased by half times, then equilibrium concentration of phosphate ions will increase by. So we are talking about the equilibrium concentration of these species. So simply if I talk about the equilibrium constant for this particular reaction, that would be the product of active masses of calcium ions, equilibrium concentrations of calcium ion as well as phosphate ion in this way. And these are the initial concentration, those we have taken. Suppose the calcium ion concentration is decreased by half time. So what will happen? But before that, you should consider that whenever we change the concentration, equilibrium constant will not change. So definitely in this case, the active mass or the equilibrium concentration of calcium ion in final condition and its product with phosphate ion in this case. Finally, these two product is also equal to the equilibrium constant. These two should be same. Now what we did, we have changed the concentration of calcium ion. It is decreased by half times. So instead of writing calcium ion, finally we can write here as Ca2 plus divided by 2, 3, and this is initial concentration we are taking here further. These are the final equilibrium concentration of phosphate ion, and these are equal to the product of the calcium ion and the phosphate ion initially. Now, if you compare these two, you will find out that the phosphate ion concentration initially is equal to here is the overall Q, and this is the PO4 3 minus, it means phosphate ion raised to the power 2 finally. Now in this case you clearly see that there are the phosphate ion initially, square is there, and that is equal to phosphate ion finally. But the 8 that was here, because 2 is here and cube, and this 2 cube comes here, that becomes 8. Now you have to take root of both the sides. Then final concentration of phosphate ion would be 2 root 2 times of the concentration of phosphate ion initially. This relation can easily be written as the phosphate ion concentration finally is equal to 2 root 2 times the phosphate ion concentration initially. And on this basis, we can say that equilibrium concentration of phosphate ion will increase by 2 root 2 times. And that's why option 2 becomes the correct option. I hope this question is clear to you. Let's take next question. Question number 75. Standard oxidation potential for the following half cell reactions are. We have these standard oxidation potentials. So what would be the reduction potential for these two cases? If we talk about the reduction potentials, definitely standard reduction potential for these two cases becomes minus 0.44 volt, and for the second reaction it would becomes plus 1.81 volt. For both of these cases I have written here the reduction potential instead of standard oxidation potential. Now the standard EMF of the cell reaction. The reaction is given here in which iron and cobalt are present, and there is the process of redox. So here, as we just want to find out the standard EMF of the cell. So this is E naught cell, and that is always equal to E cathode minus E anode. Just have a look on the reduction potentials given here. If you look at the reduction potential, you will identify that the species that you can take at cathode is cobalt with the electrode potential 1.81 volt, while the species that can be taken at anode is iron with reduction potential minus 0.44 volt. So just find out the EMF value or simply the E naught cell. That would be equal to 1.81 minus 0.44, and if you solve this, you will find out that this value is 2.25 volt. Where this 2.25 volt is given, it's correctly given here in option 4. So the answer for your question becomes option 4. Let's take next question after that.